Since now we have studied random variables through their true abstract distributions. Now, in this section, talking about statistical inference, we will see how we can experience what we observe in the real world to what we have covered since now. So that's how we see the phenomenon. In the previous section, I often talked about population, the sample space, the abstract space where the phenomenon lives. But what we get through our experience on that phenomenon is a small subset of the sample space, which is the observed sample. So our goal here, since the population, the sample space is sampled from it and through a sampling scheme, we get an observed sample, which is quite small usually. Our goal now is to use statistics, since now we have talked about probability in the population. Now we talk about statistics, and the statistics will bring us from the observed sample to the population. That's statistical inference. So the observed sample can be written as a collection of n observations. And this is typical what we get. We use the capital X only for the random variables, the function. Here, with this X instead, we described the value, the precise value we have measured, we have observed. In fact, we have observed n values, but we can think of them as realizations of n random variables. And this this sequence of random variables can be thought as an n-dimensional random variable, a unique multi-dimensional random variable. And this multi-dimensional random variable has a probability density function, and its probability distribution density function will be our statistical model that describes the population. So, knowing the sample scheme, let's look back here, and right now we will talk about the sampling scheme. Then we will approach the statistical inference. So, when talking about the sampling scheme, we can say that knowing how it's done, we will be able to characterize a little better our samples, our observed samples. For example, we can think about independent samples. If the samples are selected randomly and the observations do not depend on the values taken but the other observations. This assumption from the sampling scheme is frequently used, but sometimes is just an approximation. In fact, many phenomenon could be many samples could be slightly dependent to each other. So, since the theory for independent sample is very, very simple respect to the dependent sample theory, we will use the independent one. But we say that the dependent samples are somehow dependent to each other. For example, one extremely simple example about the dependent samples is the Markov chain. In the Markov chain, the last observation, the last random variable is dependent to the previous one, to just the previous one, not the others. That, of course, is a sort of dependence. And as I said, in the sampling scheme, we further think about the samples as independent to each other. And also, usually it's supposed that the random variables are also identically distributed. This means that x1, x2, xn will have the same probability distribution function and also the same value for its parameters. That's why, talking about, for example, the weak law of large numbers and the central theorem, we have assumed in the statement that the random variables were IID, independent and identically distributed. Here we go. That's the IID assumption, independent and identically distributed assumption. For example, here let's look at 2 dice rolling, and we sum the score of those dice. In here, we'll take in this graph we look at 1000 trials, and in the light blue histogram you can see the measurements, the frequency. In the red one, in the red line, you can see the expected results from what we can say the previous section, the probability section, what in theory should happen when rolling 2 dice. Now we have assumed independent sampling between one roll and the other, but we can't still get the exact distribution. After 1000 tries, that could be think as a lot. How many hours should I spend to do 1000 trials? And still I don't get the precise true distribution as stated by theory. So, since now we have covered the first part, from population to observed sample through the sampling scheme, and in the further slides we will assume that the distribution of the sample will be independent and identical distributed. So what we can do is that the random variable that is n-dimensional could be described as some sort of distribution that depends on maybe maybe scalar parameters, vector parameters, and parameters that are matrices. These parameters lie in what we will call the theta space, the parametric space. Since the IID assumption, these parameters are a sort of population constants that describe the process from which the population, from which we get some samples from the population. But now we look back at the other side. We want to go from the observed sample to build such a set of hypotheses and a theory to describe from the observed sample the entire population in the most rigorous and precise way possible. And there are two different ways, two tasks we can do with statistical inference. First one is parameters estimation. We can estimate from the observed sample the parameters and assign a value to them, so we will call it point estimation, or a confidence intervals. For example, I say this is equal to 0 plus minus 1, so that's a confidence interval. Are you sure about that interval? Yeah, with a confidence of the 99%. Alright, that's a confidence interval. If I say this parameter is equal as value 0, that's point estimation. We will cover in this course only point estimation. Another task we can do with statistical inference is hypothesis testing. And hypothesis testing regards about deciding whether, on the basis of the observed sample, if an hypothesis about the values of the parameters can be accepted or must be rejected. So we make an hypothesis and we test about the values of the parameters, and we test the hypothesis using the observed sample. This, what we have seen so far, were the two tasks we can do with statistical inference, but there are three ways on how we can do it. For example, we have the classical approach, the most frequent approach that is studied, and the main mathematicians that described the classical approach were Fisher, Neyman, and Pearson. Pearson, the one that made the correlation coefficient. In the classical approach, we have parameter estimation and hypothesis testing that are developed from the sample distributions of statistics. Here, the classical approach is an objectivist approach, in which we use the frequentist probability, in which, for example, in a discrete random variable, the probability of that event is looked as the fraction between the number of that particular event over the number of trials, with n that goes to infinity. So, in the classical approach, we start from this sample distribution of statistics, and we will look at only in this course about the classical approach, this approach that will refer a lot about the what we studied in the previous section about probability and distributions. But there are also another approach, the Bayesian approach. In the Bayesian approach, we still do parameter estimation and hypothesis testing, but now these two tasks are developed using an induction process. We still use the observed data, of course, but we also use a priori information. So the approach is subjectivist, and the probability is defined through the Bayesian probability, in particular using the Bayesian theorem. So again, the conditional probability here is described as, here you can see, this condition probability, the probability of the event A given B, the posterior distribution, is determined as the likelihood B given A, and this is our observed sample, times a priori distribution, what we think before seeing the results of the experiment, before the measuring. What do we think about that event A? And then we have the normalization term, since this probability must be between 0 and 1. Third, but not last, is the decision theory approach. In particular, the decision theory approach does not refer to parameter estimation and hypothesis testing. It is a particular branch of statistics, and in which in this theory what are developed are the action rules called decision rules, in which in situation of uncertainty are demanded to the analysis of the observed data and a priori information. So in decision theory we use observed data, a priori information, we mix them together to build some decision rules that will guide us in situations of uncertainty. Let's following the classical approach, let's start with the parameters estimation, particularly the point estimation. And we given a sample of n random variables, we call a function of this sample statistic. A statistic is a function of the sample. In particular, here in the scenario we are talking about statistics, not estimators. For example, a statistic is a sample mean, since this is a simple function of these two. The sample variance is also a statistic, in which this number, the sample mean, is a given. As you can see, the sample variance could seem like a sample mean, a type of mean, since the variance is the expected value of the squared of x minus the expected value of x. Here that's kind of the same, but we have not 1 over n, but 1 over n minus 1. We will see in a little bit why. So this statistic is a function over the sample, but the sample can be described through n random variables, and the function of random variables is still a random variable. This means that we can associate a distribution, a probability distribution, to this statistic, and this is called sampling distribution. For example, the simple mean. Let's look at the simple mean. It can be shown, can be proved that for a population of mean mu and variance sigma squared, so we are using IID assumptions, it can prove that the expected value of the simple mean is equal to mu, and the variance of the expected value is equal to sigma squared over 9n. But even more, for a population with normal distribution, so these xy are IID distributed, and in particular normal distributed, then the simple mean will assume the normal distribution itself with mean mu and with variance sigma squared over n. Now let's look at particular type of statistics called estimators. Why? Because those kind of statistics are meant to estimate the parameter theta. The estimator will be denoted by this at on top. The estimator, the function, takes as argument the random variables. The estimate, so when these random variables take some values, we get an estimate of the parameter theta, of course with respect to the observed sample. Since again the estimator theta hat is a statistic, then again it is a random variable, and thus we can associate a probability distribution on it. Pretty straightforward. So given a generic sample, the goal is to define an accurate estimator. And what we mean by accurate? For example, we need to measure the error between the parameter's true value and its estimate, and to try to decrease that error, to minimize that error. Which kind of error? For example, the mean square error, which is computed in this way, as the expected value of zeta hat minus, which is the estimate, minus the true value of the parameter squared. Why we are using the expected value? Again, because zeta is a number, a value, but this estimator is a random variable. So to compute the mean square error, through which values? To all the values that this random variable can take. In particular, the mean square error can be decomposed. For example, if inside this parenthesis we subtract and sum by the expected value of the estimator, and we apply some formulas, we obtain this long expression. But one term of this expression is equal to 0, because the expected value of theta is a number. So the expected of a number is the number itself. And here we get the expected of zeta. These two values are the same, so the difference equals 0. So this term goes away, and we get this one. But again, this is a constant, since this is a value, the true parameter value. This is a value, since it's the output of an expected value computation. So again, we don't need to do the expected value inside it. And we get these two terms. We will see in a bit what they mean. But first, since we have expressed our volunteer to find some good estimators, let's list some properties, some good properties of estimators. For example, we would like that the estimator not to be biased. And we say that an unbiased estimator is an estimator in which the expected value of it is equal to the true parameter for every parameter we take in consideration. Another property that we would like our estimator to have is the consistency. So given this estimator, in which we write n to describe its dependency of the sample size, and we would like that the estimator converges to zeta, to our true parameters, as n goes to infinity. So it means that given a boundary of epsilon, the value of the estimator still gets inside the boundary when we approach n to infinity. It means that it does not take at one point, at a certain point, particular value different, very different from the true value, the ground truth of the parameter itself. Third property that we will discuss in the next course is the efficiency. So looking at the unbiased estimator, we can define a new concept, the bias. And the bias will be the difference between this quantity and this quantity. Of course, if the bias is null, so the estimator is unbiased, then this quantity will be equal to 0. And again, let's take a look here. Here, inside this parenthesis, we have a bias. Oops, here I forgot the squared term. So the mean square error could be described as the variance of the estimator. That's exactly the formula. And the squared of the bias to the power of 2. An example. Why we need to define the bias and to require preferably that the estimator would be unbiased. Let's look at a stopped clock. In this particular picture, you see a stopped clock that is the best estimator 2 times per day, at 3 AM and at 3 PM. That's strange. I mean, the sentence is true, but I would not say that this estimator is the best estimator I could find. Meh, it's still a bad estimator. But how can I formally describe this thinking? Well, here the estimator is always equal to 3, but the parameter space here goes from 1 to 12. So thus the stopped clock is a biased estimator, since this relationship is not satisfied for all values of the parameter. The consistency instead says that as the number of observations increase indefinitely, the resulting sequence of estimators converges in probability to the real parameter. This means that the distributions of the estimates become more and more concentrated near the true value of the parameters, without the jumps away from the ground truth. An example. Here we have a sequence of estimators that in the picture are called T1, T2, T3, and T infinity. And the goal is to estimate the parameter which is equal to 4. A consistent estimator is an estimator that converges to this value 4. And this estimator T is in fact a consistent estimator. You start from a bad estimator with just one sample, and you get better and better since here. This is the consistency. But alright, we have defined what an estimator is and the fact that we want to do a point estimation. We have described some particular properties about the estimator that we would like to find on the estimator we build. But how to build the estimator, how to determine an estimator? Well, in the history of statistics, several methods have been proposed for estimating parameters. For example, the maximum likelihood theory, the minimum mean square error, the method of moments, and so on. Here we will look at the maximum likelihood theory. So given the observed sample, here we have just the values coming from the population. We describe a model which is, and we define this function as the likelihood function. What is a likelihood function? It's the joint probability for the sample, and this function is interpreted as a function of the parameter etc. See, so these are the proposed is our model, our inference model. We think at the phenomenon as a random variable, and we choose a probability distribution for it. But now we have to determine the parameters of that probability distribution. This sort of unknown probability distribution, described with the density function, is a function, in fact, of the parameters, and indirectly, but that's it. So now, since we have an observed sample, we can compute the probability density function with respect to the value, but the parameter still remains unknown. That's why we interpret the likelihood function as a function of the parameter theta. We can write this because the jump probability can be decomposed since we assume that the sample is IID. What's our goal? Well, our goal is to determine the maximum of the likelihood function, and we build the maximum likelihood estimator as the value of the parameter that maximizes the likelihood function. But why we want, let's go back a little bit, why we want to maximize the likelihood function? Well, the likelihood function here, remember, is the joint probability of the sample. So finding the maximum of the joint probability with respect to the unknown parameter, the unknown value of the parameter, means that we are assuming that the observed sample, what we have seen, what is provided to us, is the one in which those samples were the ones with the highest likelihood to be observed. It's some sort of philosophical, this theory. The sample we get is the one that in the population, in the sample space, had the highest likelihood to be observed. But alright, so the sample I got was the one with the highest likelihood, but I still have to determine a parameter for that distribution. So I choose the parameter that maximizes the global likelihood to get that sample. That's how I build the maximum likelihood estimator. How can I find then this estimator? Well, I need to find the maxima of the likelihood function, and I can do it by computing the derivative, because I know that if theta is the value for which L assumes the maxima, the maximum value, it means that in that point the derivative of L is equal to 0. But we will see that it's not true the vice versa. If the derivative is equal to 0, it does not mean that we are looking at the maximum. But let's start with this sentence. Why the derivative here should be 0? Well, because this could be a saddle point, a maximum, or a minimum, where the slope, the derivative, is equal to 0. For example, here we have a minimum, a maxima. As you can see, the derivatives are greater than 0 and smaller than 0. And we have a saddle point when we have derivative equal to 0, but no maximum or minimum. And that's why looking at a point where the derivative of the likelihood function is equal to 0 does not mean that we are looking at the maximum of it. First of all, because we can look at local minimum, a saddle point, or even at a local maximum, and not at the global maximum, which could be, for example, this one, A global maximum, of course, is also a local maximum. Let's look at the maximum likelihood theory in practice with a Bernoulli distribution, the simplest one. Our probability mass function could be written in this form. X, what's the probability of x equals to x? Well, 1 minus p if x is equal to 0, p if x is equal to 1. Alright, so we can simply write this probability in this form. P of x times 1 minus p to the power of 1 minus x. Why? Because if x is equal to 0, this is equal to 1. And this is equal to 1, and we get 1 minus p. If x is equal to 1, we get p here, 1 minus p to the power of 1 minus 1, so to the power of 0. So this can be cancelled since it is equal to 1. So let's imagine a sample of n observations of a Bernoulli distribution, and we want to estimate our unique parameter, scalar parameter here, the parameter p. What we have to do then? We have to write the joint probability as the product of the marginals, since we are in a IID assumption. That's our product. This is what we have seen for one random variable. Then we do the product of the n observations. This is our likelihood function. Now it becomes the most onerous part about the calculus. But first, since we are dealing with products, is very difficult. We can compute the logarithm of that product to let it become a sum of logarithms. But why we can do it? Well, the logarithm is a monotonic function, so maximizing the log likelihood function leads to the same results as using the likelihood function. The log function just rescales the value, but keeps the maximum values and the minimum values. So for simplicity, we will refer here to the log likelihood function as the log of the likelihood function. Again, the logarithm of a product is the sum of the logarithms. And again here we have a product between this term and this one. We can split them, and then we know that the logarithm of something to the power of xy, for example, is equal to xy times the logarithm of that something, of that p. So we get this expression, which is reported here. This will be very useful in the next course. Now, and this can be seen as the log likelihood for one sample, because this sum would go away, and this is the log likelihood function for one sample. But we can, since we are considering a sample of n observations, we can do more. Get at those results. I will skip those calculations, and we will get to the point in which we will compute the derivative of the log likelihood function with respect to p and point out this equal to 0. we substitute the log likelihood with the values we have found so far, we do the calculation, and we get that the estimator is equal to just the average of xy. Here I written the estimator as a function of the random variables. You can see the capital X. If I would explicit the estimate, I would have written p at as function of x1 xn, and then here I would have written xy's, not capital. How can I know that this is the estimator, since I use the derivative and say that this is the maxima? Well, I can compute, for example, the second derivative. But I tell you that this is the value, the estimator we were looking for. Moving on, let's take a deep look about hypothesis testing. In hypothesis testing, we do an hypothesis on parameters. In particular, this H0 is the null hypothesis, and we think that the parameter is inside this omega space, inside the parameter space. We say that this hypothesis is accepted if the sample lies inside an acceptance region, inside the sample space. Instead, if the sample lies inside the R region, the rejection region, then in fact the true value of the parameters will lie on the complementary of omega in the parametric space. So again, A means the acceptance region and R represent our rejection region. We accept our null hypothesis that theta lies inside omega only if the sample lies inside the acceptance region. So in the hypothesis testing, the goal is to find the optimal regions of omega for defining the acceptance regions, the acceptance region and the rejection region. We will not go into detail. This is just an overview of hypothesis testing. But when deciding to accept or reject the null hypothesis, H0, you can make two types of errors. In the type 1 error, you could reject H0, the hypothesis, but the hypothesis was true. In the type 2 error, instead, you accept the hypothesis, but this is false, and you don't know it. This can be described through this table, in which here we have the conclusions from our statistical analysis. We do some sort of analysis, and then we apply the hypothesis testing to test if this match with the true state of nature, which are our rows. So if in reality, the ground truth, the null hypothesis is true, and we accept the fact that we accept the null hypothesis, then we came to the correct conclusion. The same if we reject the null hypothesis and the null hypothesis was effectively false. But we do a type 1 error if we reject a true hypothesis, and we do a type 2 error if we accept a false hypothesis. Thanks to the statistical inference, now we are able to estimate the parameters of the statistical distribution underlying a phenomenon. We can approximate them, but this is enough to build some data science tools.